Lesson: Evaluating neural network performance, metrics and techniques. Evaluating the performance of a neural network is a crucial step in the development and deployment of machine learning models. It involves a systematic approach to understand how well a model performs in predicting outcomes and to identify areas for improvement. This process is underpinned by various metrics and techniques, each serving different purposes and providing unique insights into model efficacy. The evaluation process is not only an academic exercise, but also a practical necessity that impacts decision-making in real-world applications. The first step in evaluating neural network performance is selecting appropriate metrics. Different types of problems require different metrics. For binary classification problems, common performance metrics include accuracy, precision, recall, F1 score, and the area under the receiver operating characteristic curve. Accuracy is the most straightforward metric, measuring the percentage of correct predictions. However, it can be misleading in imbalanced datasets where one class is more prevalent. Precision and recall address this by focusing on the positive class. Precision measures the proportion of true positive results in all positive predictions, while recall measures the proportion of true positive results in all actual positives. The F1 score, the harmonic mean of precision and recall, provides a single metric for balancing precision and recall. In multi-class classification problems, metrics such as macro-averaging and micro-averaging are used to provide an overall performance measure. Macro-averaging computes the metric independently for each class and then takes the average, treating all classes equally. Conversely, micro-averaging aggregates the contributions of all classes to compute the average metric, favoring larger classes. For regression problems, metrics like mean absolute error, mean squared error, and R-squared are commonly used. MSE is particularly useful for penalizing larger errors, while R-squared provides insights into the proportion of variance explained by the model. Beyond metrics, visualization tools play an essential role in evaluating neural networks. Confusion matrices, for instance, offer a visual representation of the performance of a classification model, depicting true positives, true negatives, and false negatives. Visualization of ROC curves and precision recall curves can also offer insights into the trade-offs between different types of errors and the overall performance across thresholds. These visual tools are integral in diagnosing where models may be falling short and can guide further refinement. Practical tools and frameworks facilitate the implementation of these metrics and techniques in real-world scenarios. Python libraries such as scikit-learn provide comprehensive modules for calculating performance metrics and visualizing results. TensorFlow and PyTorch, the leading deep learning frameworks, also support integration with these libraries to streamline the evaluation process. For instance, using scikit-learn, one can easily compute an array of classification metrics with functions like classification report or ROC-awk score. These tools not only simplify the computation of metrics, but also allow for quick comparisons between different models or iterations of a model, enabling data scientists to make informed decisions. In practice, evaluating neural network performance is an iterative process. Model validation techniques, such as k-fold cross-validation, help in obtaining a more reliable estimate of a model's performance. Cross-validation involves partitioning the data into k subsets and training the model k times, each time using a different subset as the validation set and the remaining data as the training set. This approach minimizes overfitting and provides a more comprehensive assessment of the model's generalization capability. Implementing cross-validation in Python with scikit-learn is straightforward, using the cross-val score function, which automates the training and evaluation process, providing a mean score and standard deviation across folds. Hyperparameter tuning is another critical aspect of model evaluation, directly impacting performance. Techniques such as grid search and random search help in finding the optimal set of hyperparameters that maximize the model's performance on the validation set. Grid search exhaustively searches through a specified parameter grid, while random search samples random combinations, which can be more efficient with large parameter spaces. Both methods are supported by scikit-learn, offering an easy-to-use interface for hyperparameter optimization. Case studies illustrate the real-world application of these techniques. For instance, in the healthcare sector, neural networks are employed to predict patient outcomes using electronic health records. Here, precision and recall become crucial metrics due to the high cost of false positives and false negatives. A study might reveal that while a model achieves high accuracy, its recall is low, indicating that it misses many positive cases. By adjusting the classification threshold or rebalancing the dataset, practitioners can improve recall, thus enhancing the model's utility in a clinical setting. In conclusion, evaluating neural network performance requires a multifaceted approach that encompasses appropriate metric selection, visualization of results, and the use of practical tools and frameworks. These methodologies not only provide insights into how well a model performs, but also highlight areas for improvement, guiding the iterative process of model refinement. By leveraging these techniques, professionals can enhance their proficiency in neural networks, addressing real-world challenges with confidence and precision. The integration of tools like scikit-learn, TensorFlow, and PyTorch, along with techniques such as cross-validation and hyperparameter tuning, empowers data scientists to build robust, reliable models that deliver tangible results across various domains.